Hello, this is Malachi Bishop, and this is RC-750, Rehabilitation Counseling Research and Program Evaluation. This is week 5, and we will be talking this week about understanding concepts of descriptive statistics and understanding concepts of inferential statistics. And in this section, first section of week 5, we will be focusing on descriptive statistics. Sometimes the purpose of research is to describe some characteristics of a sample or population, or the distribution of variables in the sample. We're going to look at some examples, but essentially what we're saying with descriptive statistics is that they allow us to describe the sample or population or the characteristics of the participants in the sample or population. The purpose of descriptive statistics, like the name suggests, is to accurately describe and summarize data from a population. Sometimes when the population is manageable or when we can identify all the people in the population, but probably more frequently to describe and summarize data from a sample of the population. And when we talk about descriptive statistics, we're talking about describing the sample or population in terms of two characteristics. The first is central tendency, which includes the mean, median, and mode. And then the second is variability, means how the data are spread out, the spread of the data. And this includes the range, variance, and standard deviation. So we'll be looking at these measures of central tendency and variability. So in terms of the measures of central tendency, we're talking about the mean, the median, and the mode. The mode is simply the most frequently occurring number in the data. So it's the number that shows up the most. The mean is the arithmetic average of a group of scores or observations. And I'm sure you're all familiar with the concept of calculating the mean, but basically it is this symbol right here. The sigma stands for sum, by the way, just so you know that. So it is the sum of all the observations or scores divided by the number of scores or observations or people that you have in the group. So for example, the mean of this group of numbers here, 28, 26, 24, and so on. To find that mean or arithmetic average, we would add those up. We would find the sum, which is 178 in this case, and then we would divide that by the number of observations, which is 8. And so our mean would be 178 divided by 8 equals 22.25. So the mean for this group of numbers would be 22.25. And the mean is probably the most frequently reported of the measures of central tendency. The other one that you will see frequently reported in conjunction with the mean is the median. And the median is the place in the distribution of scores that divides the top half from the bottom half, or the value that occurs in the middle of the distribution. And the median is the center point in a set of numbers. To calculate the median by hand, again, I'm sure you're probably familiar with this process, but just briefly, let's look at how this works. To calculate the median, you line up the numbers in ascending or descending order, and then you check to see which of the following two rules apply. If you have an odd number of numbers, then you can apply rule 1, which is essentially to say that the median is the center number, the number in the middle. So for example, in the numbers 1, 1, 3, 4, 9, we have 5 numbers there, so it's an odd number. We simply take the number in the middle of that distribution, which is 3, and 3 is the median in that case. If you have an even number of numbers, then the median is the average of the two innermost numbers. So for example, in those numbers 1, 2, 3, and 7, we have 4 numbers, so we have an even distribution there. Even number of numbers in this distribution, and the two innermost are 2 and 3, and so we would take the average of those two innermost numbers, and that would be 2.5. Let's look at one more example. In this sample, this is the sample we looked at on that last slide. There are 1, 2, 3, 4, 5, 6, 7, 8 numbers in this distribution, so we know it's an even number, and we're going to have to take the average of the two centermost numbers in the distribution, and they are both 23 in this case, so we know in this case the median number would be 23. So that's just a little review of how to calculate the mean and the median, and remember the mode is just the most frequently occurring number. For some research questions, central tendency is the most meaningful form of statistic. For example, I'm going to show you a couple of examples of rehabilitation counseling research. One is actually about rehabilitation counseling research, and then another from some research that I'm doing on specialized housing among people with disabilities, where the questions in that latter study are basically we just want to find out, because we don't know what the need for specialized housing is in this group of people that we're studying, and it happens to be a group of people with multiple sclerosis. So we came into this study with the question, what are the characteristics of this population, and how many people in this population need specialized housing or housing modifications. So I'm going to show you some descriptive statistics for that project that we're working on. First, let's look at this idea of rehabilitation counseling research and why measures of central tendency were useful in this question. This was a study by Schultz, Cook, and Kontosh fairly recently in 2007, and they were looking to establish research priorities for rehabilitation counseling. And so what they did is they identified, through another study that they did, a lot of potentially important research topics, things that rehabilitation counselors should be doing research on. And then they asked members of the rehabilitation counseling profession to rate the importance of these topics, so we could have an understanding of what people in rehabilitation counseling thought was the most important thing to study and what was less important to do research on. So they said rate the importance of these topics of research from 1 to 8. And you can see here we have our central tendency descriptive statistics represented, the mean, median, and mode. And so here we have a question where the descriptive statistics are very helpful in helping us to understand the data. So we have these different potential areas that we could do research in: rehabilitation interventions, rehabilitation outcomes, consumer involvement in rehabilitation, and so on. And you can see the rankings there, but you can also see the mean of the ratings that people gave these things. And so that's the average of the ratings, and then you can see the median rating, and then the mode, which is the most frequently identified rating. So most people identified rehabilitation interventions as the most important topic, for example. Most people identified rehabilitation outcomes as the second most important topic. So here's an example of a rehabilitation counseling research study where the central tendency statistics were very important in helping us understand the data. Here's some data from the specialized housing research that we are doing. We have a large sample of over 5,000 people, and some descriptive percentiles here, but I want to highlight here the mean age of this population was 54 years old, 54.1. I'm also providing the standard deviation of about 10 years here, and we're going to look in a minute about why it's also important to include descriptive statistics that talk about the spread of the data. So we'll come back to these figures in a minute. But most of the time, in addition to the measures of central tendency, we are also interested in the variability of the data, or how spread out the distribution is. To understand what a sample or population really looks like, we actually need to know both the mean, so we need to know about the central tendency, but we also need to know about the variability of the distribution. Mean is not enough. For example, to show you why this is the case, I did a study a few years ago where I measured teachers' attitudes about epilepsy on a scale that ranged from -20 to +20. -20 were more negative attitudes, +20 more positive attitudes towards students with epilepsy and about epilepsy in general. If I told you that the teachers' attitudes about this disability were right at the mean of 0, what would you know about how the scores of the teachers were distributed? And the problem is, with just the mean, you really don't know. The scores could look like this, for example. Maybe every single teacher in the sample scored a 0, and that would give us a mean of 0, so their score came right up in the middle. That could be the case. Or there could be a limited distribution of scores around 0, right in the middle of there. That could be the case. You could have a bimodal distribution, where about half of the teachers scored on the negative side of the scale, and about half of the teachers scored on the positive side of the scale. And when you average these out, you would end up with a mean of 0. So you could have a distribution that looks like that. And you could have a distribution that looks like this, sort of spread out from +20 to -20, again with a mean of 0. So without that additional information about the variability or the spread of the data, then you don't really know, based just on the mean, what the distribution would look like. So we also have to include those measures of variability, and these include the range, variance, and standard deviation. And again, I'm expecting that your background has included some use and some learning about these concepts of range, variance, and standard deviation, but I'm going to briefly describe how these work. So the range is a relatively crude indicator of variability. That means it's not really very informative. What it tells you is the difference between the highest and the lowest numbers. So it's just the difference between the lowest number in set A, the lowest number is 93, and the highest number, 100. So the range of set A would be the difference between 93 and 100, or 7. Now this range of scores in set B looks to be more spread out. So the difference between the highest and the lowest number would be 10, and 100 would be 90. So we can tell by knowing the range that this set B is more widely distributed, more spread out. The scores in that set of data are more spread out. So it tells us something, but it's not terribly informative. The variance is a bit more informative. The variance is defined as the average squared deviation of each score or measurement from the mean. So it includes all the scores rather than just the two that the range tells us about. Variance describes the distribution of all the values because it includes all the values in its calculation. And it is the mean of the squared distance of each value from the mean. So let's look at what that means in terms of calculating the variance. We have this formula here. Again, the sigma symbol here is sum. So for this formula for variance, it says in order to find the variance, we take the sum of each individual score difference from the mean, so that the sum of the difference of each individual score from the mean squared, and then you divide that sum by the number of observations. So if we have 4 scores or 4 observations, 4, 7, 5, and 8, that's our data, and we would first calculate the mean, and the mean of this set of data would be 6. So to calculate the variance, we would first find the differences of each individual data point from the mean. So 4 minus the mean of 6 gives us -2. 7 minus 6 equals 1. Difference between 5 and 6 would be here. 5 minus 6 would be -1. And then 8 minus 6 is 2. So we're subtracting the mean from each of the observations. And then if you added those up, -2 plus -1 would be -3, and then 1 plus 2 would be +3. If you added those up and summed them to get their average distance from the mean, we would actually end up with 0, and that doesn't work. So what we do is we square those differences. So we square all of the -2, and that becomes a +4. We square 1, 1 squared is 1, -1 squared is 1, and then 2 squared is 4. So by squaring, we've created a set of positive squares here, and we sum these, and we come up with 10. So now we have the sum of the differences between the mean and each individual score squared, which is 10 in this case, and we're going to divide that by the number of observations, 4, and we end up with a variance of 2.5. So the variance is the average squared deviation of each score measurement from the mean. It provides us more information than the range, because it tells us about the impact of all the scores in the set of data. Standard deviation is the statistic that you'll see much more frequently, because it is much more useful statistic than the variance. So you'll generally see the standard deviation, and the standard deviation is really just the square root of the variance. So this corrects for that squaring that we did in calculating the variance. So the formula for calculating the standard deviation is just the same as the variance, only we take the square root of the variance. So the square root of the variance in that problem we were looking at on the last slide, where we came up with a variance of 2.5, the standard deviation would just be the square root of that, which is 1.58. That's just in case you were wondering. The standard deviation has a number of useful properties in normal distributions. What's a normal distribution? If we measure people or participants on some characteristic, when we're talking about a lot of psychological characteristics, if we measure a lot of people on a psychological characteristic on an interval or ratio scale, if we measure enough people on a scale like that, and usually enough is around 100 and then more than that, then you start to see the data distribute normally in the shape of a normal curve. And again, I'm assuming that this is an idea that a lot of you are already familiar with from your previous math, psychology, and so on courses. But we'll look at a normal curve in just a minute to show you what I'm talking about. If you do have data that are normally distributed in a normal curve, then knowing the standard deviation provides you with a lot of information. You will know that about 2/3 or 68% of the cases will fall within one standard deviation of the mean. About 95% of the cases will fall within 2 standard deviations of the mean. And almost everybody, almost all the data, about 99.7% of the cases will fall within 3 standard deviations of the mean. So here's that normal bell-shaped curve I was talking about. And on this curve we see the mean score would be this line in the middle. And you can see the standard deviations are identified here. 1 standard deviation above the mean, 2 standard deviations above the mean, and so on. And then 1 standard deviation below, 2 standard deviations below the mean. And you can see that about 1/3 of the population is located here, in this area here, and about 1/3, 34.13% of the population in a normal distribution would be located here, 1 standard deviation below the mean. So within 1 standard deviation above and 1 standard deviation below, we have about 2/3, or about 68% of the population. And then within 2 standard deviations in either direction, we would know that we would find about 95% of the population, as I said. So knowing the mean and the standard deviation, and knowing that the data are normally distributed, we can make a lot of informed guesses about what the distribution looks like. Let me show you another example. And this is going back to that specialized housing data I was talking about earlier. So we know the mean age is about 54 years old, and we know the standard deviation is about 10 years. So this is I went ahead and graphed the distribution, and you can see it's not quite as pretty as that normal curve, this bumpy sort of mountain here, but it's beginning to approximate, or starting to look like a normal curve. It's pretty close when we look at the ages in years of all the participants, and the number of people in each age. So we see this mean line here around 54 years old. Most of the people are going to be around that age, and we know that about 2/3 will be within 10 years either side of that, +1 or -1 standard deviation. So in other words, if we have a large enough sample that we can assume, and here we can look and see that we have enough people that the data have begun to distribute in the fairly normal looking bell curve here, and we know the mean and standard deviation, then we can make some assumptions and know some things about the data. We know that about 2/3 of the population are going to be between 44 and 64 years old. Let's take a look at how it actually breaks out. This is a graph of that same data. Here we have the 50 to 59-year-olds. Here are the 40 to 49-year-olds and the 60 to 69-year-olds in the yellow, and you can see the majority of the population is falling within that 2 standard deviations away from the mean of 54. So we knew already, just from looking at that data, that the vast majority of the people in this sample were going to be within 2 standard deviations of the mean, about 95% of the people. And here we can see that that's just about how it works out. Most of the people in this study are between 34, and that would be 2 standard deviations below the mean, and 74, which would be 2 standard deviations above the mean. The last thing I wanted to talk about in terms of distributions was this idea of skewed distributions. I showed you a distribution there of a large set of data that was fairly normal, and we could do we can have confidence in doing some inferential statistics with a distribution like that, because as you read in the text, and as we will be talking about shortly when we talk about inferential statistics, some statistics require that your data is normally distributed, but your data don't always work out like that. Sometimes you have skewed distributions. You can have a negatively skewed distribution in which most of the scores are high, but there are very few low scores. And then you can have a positively skewed distribution where most of the scores are low, but there are very few high scores. Let me show you what they look like, and we'll talk about some examples. Here we have a negatively skewed distribution with an elongated tail at the left and more data on the right in this distribution. Most of the population, most of the sample is at a higher score, and then a few people with lower scores at this tail end. And an example of a distribution like that is actually quality of life, for example. If you ask people about their quality of life, most people, the majority of people by far, will tell you that their quality of life is above average. And when you graph data about quality of life, you tend to get a distribution that looks very much like that, negatively skewed. Most people above the average. Your data could also be distributed positively, which means most of the scores would be at the lower end and then a few scores at the higher end of the range. So positively skewed data, that might be a very difficult midterm exam or something like that. So most of the class scored at the very low end and just a few people scored at the higher end. So it's expected with some variables that your data will distribute along these shapes. And the issue there is when you are using inferential statistics that rely on normal distributions, it's important to evaluate whether your data are close enough to normally distributed that you can use the statistics that you want to use. So that will conclude our discussion of descriptive statistics, and in the next section we will get into inferential statistics.